Hello, everyone. Welcome to this short talk on assessing the reliability of biometric authentication on virtual reality devices. This paper is a part of IJCB 2024. Uh, In this talk, I will be talking in two parts. The first part is about creating a new periaplar dataset, which is called as VR Biom, that is virtual reality device dataset for biometric applications. To give an overview of the dataset that we have created, the VR BIOM dataset consists of 900 bona fide videos and more than 1100 presentation attacks. This dataset was captured using a Meta Quest Pro virtual reality headset, which is designed by Meta. In this kind of applications, we cannot have frontal views of the iris region because the camera is fit on the surroundings of your devices. So this dataset consists of non-frontal views, and we have specifically included variations in the gaze and eyewear, that is glasses, for bona fide recordings. And for the attacks, we have considered fake eyeballs, different types of 3D mask, as well as printouts of periaplar images to construct different types of attacks. We also created a small custom app, which was called as Meta Quest Pro to capture a dataset. It helps us in providing a simple user interface that helps us in providing a specific naming convention for the file to be used. At the same time, it also helps us in connecting the device and the recording workstation using the underlying API. So when our subjects came to us, we informed them about the project and also obtained their consent for the data to be recorded and to be used for research applications. So here are some of the samples of the bona fide recordings. Here we have three gaze conditions that you can see if you look column-wise. Each column consists of steady eyes, the moving eyes, and partially closed eyes. And row-wise, you can look at the examples of subjects without glasses and subjects wearing glasses. If you look at the combination of all these variations and three repetitions of each, we have total of 900 such short videos of 10 seconds each, which have been recorded at the rate of 72 frames per second. Coming to presentation attacks, we have 6 types of categories. You can see each category represent a sample in a corresponding column, starting from mannequins, followed by two different types of rigid masks meant of real people. The fourth column represents samples from generic masks. Fifth column is a custom-made mask of silicon, which of course belongs to a real person. And finally, we have print attacks, where we have recaptured some of the prints that of real people and use them as the attacks. Here, what you see in the first row is the attack instrument captured in the normal or RGB camera. And second and third row represent the recordings where the attack instrument was kept without glass and followed by the one that was kept by wearing fake glasses. Just to inform you that this dataset is publicly available for non-commercial research purposes, and it can be used for applications such as biometric authentication using iris as well as periocular regions, then detecting presentation attacks, and you can also use it to do any semantic segmentations that is meant for analyzing your biometric research. Now let's move on to the second part, which is assessing the presentation attack detection capabilities of this dataset. So why do we want to do this? First of all, we need to understand that the virtual reality devices are finding more and more applications, and which may also include biometric authentication. When we speak of authentication, it is important to have the system that resists spoofing attacks, or which is tolerant, which is robust to the detection of such attacks on the sensor of the camera, and which is why we are going to assess the performance of PAD on the dataset that I just described. So to benchmark the performance of the VR Biome dataset, we have used the following experimental setup. we consider two different architectures, one based on the residual architecture, that is ResNet with 34 layers, and second is a mobile FaceNet, which is a small architecture, but which is specifically designed for handheld devices due to their small size and low memory footprint. We considered three different training configurations. First is from scratch, where the backbone and the classifier both were trained from scratch on the train partition of the dataset VR biome. In the second configuration, we kept the backbone fixed, which was we obtained the pre-trained model from the internet, and we classified the only classifier was trained on the VR biome dataset. In this case, the classifier is binary because we are dealing with PID versus bona fide classification. And in the third case, we obtained the pre-trained backbone from internet, but the backbone and classifier both were trained or fine-tuned on the VR biome dataset. To assess the performance of PID, we used metrics such as APCER, BPCER, and ACER, which indicate the error in detecting attacks, error in detecting bona fides, and average of both the errors respectively. Some more details about the experimental setup. We split the data set into partitions that were non-overlapping in terms of the subjects, that is training, validation, and testing. The images were resized to 112 by 112 pixels, which is the requirement of the pre-trained models that we have downloaded. And for augmentations during training, we randomly flipped the images in horizontal direction, as well as we rotated the images up to 20 degrees, which was also done in the random manner. So here are some of the results that we have obtained. In this case, each of the row represents the specific combination of configuration and backbone, followed by the EER that was used to obtain the threshold from validation partition, and everything else that you see are the APCER and BPCER, ACER metrics obtained on the test partition. The columns in the blue represent different types of attack instruments. You can see more details of those in our paper. These instruments are same as what I described in the previous slides, such as mannequins, rigid masks of different couple of types, custom masks, generic masks, and finally print attacks. So here what we can observe is, in each case, the mobile FaceNet has performed better than its ResNet counterpart. Since all the numbers that you see here are error values, the lower values are of course desired. In case of training from scratch, we obtained reasonable performance, which is possible in the case because the data sets is not large enough to thoroughly train the model properly. In case of fixed backbone, the attacks rate were relatively higher, especially for ResNet. The attacks rate are close to 20%, which means every 1 in 5 samples was treated wrongly. And these numbers were quite low for mobile FaceNet, but still you can see that they're relatively higher compared to what it has performed when it was fine-tuned. Fine-tuning seems to give the best performance, which possibly means because it allows us to use the rich features that have been learned on other third-party data sets. At the same time, we are free to fine-tune the complete network, which is classifier and backbone both, for the specific application of detecting attacks on VR dataset. In the best case scenario, we obtained on the mobile FaceNet when everything was fine-tuned, and the overall average error rate was as low as 3%. However, you can also observe that if you look at the APCER of different PA instruments, that is, for example, mannequins is the first one, it seems to be consistently difficult to detect mannequins, even when the entire network was fine-tuned for it. And attack rates could be as 30% or even close to 50% when the backbone was fixed for ResNet, which means like every third attack is detected as a bona fide. Similarly, a certain type of rigid mask, which is under the column with number 4, also seems to be difficult to detect across all combinations of training as well as both the backbones. On the contrary, a couple of other attacks are relatively easy, and numbers also seem to be zero, which means the attacks were detected completely well by the corresponding backbone. Now we can also have a look at the receiver operating characteristics of the same results. Here, the plots in green correspond to the ResNet backbone, and the plots in blue correspond to a mobile FaceNet. As you can see, it's meant for each of the training configuration we have. The ideal condition, let's say where the system is perfect, is represented by a plot which is parallel to x-axis at y equal to 1. That is at the top of the plotting area. In each of the three plots, it can be observed that the mobile FaceNet, the one in blue, has consistently outperformed the plots in green, that is the ResNet counterpart. We can also see that the third approach, which is when everything was overall fine-tuned, the performance seems to be consistently better compared to other two training methodologies that we tried. So to summarize, we observed that mobile FaceNet backbone consistently outperformed ResNet 34 despite its quite smaller size. In terms of training methodologies, fine-tuning the backbone and of course training the binary classifier has shown the best performance. And we have able to achieve ACER, that is average classification error rate, as low as 3.11%. And speaking in terms of different types of attack instruments, detecting mannequins and certain rigid masks has been quite challenging for all the configurations that we have tested. Some of the challenges that we have seen, in case somebody wants to work on specifically iris on the iris region, not the complete periocular region, you will first have to detect this eye or iris part, and detection was seen to be quite poor, especially because the views are non-frontal. Secondly, the data set is captured in infrared, which while the backbone that was fixed was obtained, it was trained on the RGB data. To understand or to address the domain shift, we need to have some kind of transfer learning, or we probably need to build VR data sets that are large enough that we can use them to train the model quite well. And finally, we also see that while some attacks were detected quite well for, let's say, each of the configurations or each of the backbones, it was very difficult to get a good generalization capability of models. So handling different types of attacks is still a quite of a challenge. To summarize, we have created a first publicly available VR dataset which features a non-frontal periocular recordings. It's taken from the real commercially available data capture device. To include realism in the samples, we have variations in the gaze as well as in terms of eyewear. And for attack, also we have considered different types of attacks. We have also used fake eyewear for the attacks too, to make it more realistic and challenging. This work is meant to highlight the importance of detecting presentation attacks on VR-based biometric systems. Then talking about the results, even when we see that the attacks detection could be quite good with average error of about 3%, the APCER, that is attack presentation classification error rate, could be as 33% and even more, which means that every one of the in 3 attacks can be passed or can be considered as bona fide, which means how open-ended the problem is, and we need to work on improving, bringing this number down across different categories of the attacks. As well as we need to design better algorithms to handle the non-frontal views and a relatively low resolution of the images in case we want to build good recognition systems as well. Finally, I would like to thank the Meta program, which is called as Towards Trustworthy Products in AR, VR, and Smart Devices for their funding support. Also, thanks to our data collection team. I would also like you to download the VR biome dataset as well as the Python code for assessing the PAD, which consists of the experiments that I just described. The QR codes for each of the dataset and the GitLab repository are on the screen. Thank you for your attention.